Hello, everyone. My name is Lin Shen. I'm a professor at the Civil Engineering Department at the University of Hawaii at Manoa. In this video, I will share our experience on large-scale applications of cement-free alkali-activated concrete with optimized cost and performance. Here shows the outline. First, I will introduce what is AEC and why AEC is the sustainable materials. And then I will discuss how we analyze the precursors, such as fly ash, slag, and red mark. And then I will show you how we monitor the kinetic reaction of alkali activation process using Raman spectroscopy. And then I will briefly show you the performance evaluation in the concrete lab, and then in the field applications. So concrete is made by mixing Portland cement, which is a powder form, with small amount of admixtures, some water, some sand, we call that fine aggregate, and also larger stone, we call coarse aggregate. Mix all these five materials together, we have concrete. 6 to 8% of all man-made CO2 comes from cement production. Annual cement production is 4.6 billion tons. And for every tons of cement, if you produce 0.85 tons of CO2. So annual CO2 from cement production is around 4 billion tons, which is equal annual cement CO2 emitted by around 600 million cars. In April last year, Hawaii became the first US state to declare climate emergency. The resolution calls on government to make choices that will enable a more sustainable future. It goes as far as us to ask for a ban on public and private investment that would make climate change worse. And this is the interview of Mr. Bill Gates last year, and I just quote here, cements over 6% of worldwide carbon emissions, and yet we do not have a way of doing that is clean, that does not cost dramatically more than twice the price. I believe in many cases, we can do that sometime even much better than that, as I will show you in a moment. Cement production extracted around 3 billion tons of raw materials, including limestone, sand, clay, and so on, every year from the earth. And at the same time, industry waste from coal burning process and steel aluminum production produce hundreds of million tons of fly ash, slag, and red mark every year. This is the video I took while I visit one of the largest aluminum producer in the world, Xinfa Group in Shandong province in China. And you can see the polluted river from the red mark. This is another video of coal burning power plant I took in Xinfa last year. And this table shows the production, utilization percentage, and carbon footprint of cement, fly ash, slag, and red mark. Okay. And because fly ash, slag, and red mark are waste materials, they will not have any more carbon footprint when they replace Portland cement. And because of the low utilization percentage, right now we have billion tons of fly ash, slag, and red mark landfill already. So AAC or alkali-activated concrete using waste materials such as flash, slag, and red marl, plus small amount of admixtures, we call that alkali-activated admixtures, plus water, sand, and coarse algae mixed together, we have concrete. So comparing normal concrete and AAC, we can see both normal concrete and AAC use water, sand, and coarse algae. They all need small amount of admixtures. The major difference is AAC use waste materials instead of Portland cement. So when we replace Portland cement with flash, slag, or red marl, we help reduce the billion tons of CO2 from cement productions. We also help reduce the billion tons of excavation of raw materials such as limestone and clay. We also help reduce the billion tons of flash, red marl, and slag already landfilled. So we could have cleaner air, water, and soil. So here is a nice picture I took about my house in Hawaii. Okay. What I want to see here is fighting climate change is a global effort. It must be a global effort, and we should work together to preserve our planet. Alkali activation is a reaction of solid aluminum silicates, we call that precursor, such as flash and slag, under alkali condition, using alkali activator such as sodium hydroxide and sodium silicate. So mixed together, we can produce hardened binder. And AAC is not a new concept. It dates back to more than a century years ago. And based on chemistry of precursors, we have high alkali AC, low calcium AC, and blended system. And for high calcium AC, the reaction products including cash or aluminum substitute disorder topomeride like CSH. We could have AFM, which is a classic phase in Portland cement, among other hydration products. And for low calcium AC, we could have the famous geopolymer. We also call that NASH, N-A-S-H. We have two types of NASH, GL1 and GL2, plus we could have calcium hydroxide. And then for blended system and intermediate calcium, we could have coexistence of CSH and NASH. And also depending on the pH level, we could have different type of reaction products. The ultimate goal of this research is large-scale applications of high performance and also economic AC using standard equipment and a simple mixing procedure. We try to optimize the concrete mix design, balancing performance and cost by studying these precursors more accurately, and also by monitoring kinetic reaction using Raman spectroscopy. Next, I will show you the precursor analysis. We use flash, different type of red marl, and slag. And here shows XRF, which can give us the basic information of percentage of different type of oxide. However, XRF alone is not enough. Okay. We also use XRD, which is X-ray diffraction, to give us the idea of the percentage and type of crystalline phases. By combining XRD and XRF, we could have a much better estimation of the reactive phase and also the non-reactive phase. We also call that amorphous phase and the crystalline phase, as well as the idea of the type and the strength of the crystalline phases. And here shows the AES flash. AES flash is coming from Hawaii local power plant. The flash has pretty low quality compared with commercial flash. As we can see from here, the scanning electron microscope, AES flash is not a classic spherical shape, and it has less reactive phases and also larger particle size. Okay. And here shows commercial flash. It has classic spherical shape, much higher quality, very reactive phases. And here shows the major reactive phases of different type of Raman samples, including reactive calcium oxide, silica, and alumina. And based on that, we can predict the final hydration product of the Raman concrete based on these components. And also with the help of this ternary diagram showing us the percentage of reactive calcium, silica, and alumina. The predicted final product will also verify by XRD. In this example, we show the XRD of Raman and Raman concrete at 1 day, 7 day, and 28 days. By comparing these 4 peaks, we see mostly hydration product is CSH. We could also have some small amount of NASH. So this Raman AM generate CSH mostly, as we can see from the peak here, a big change in CSH. And its crystalline phase is hydrogonate. So hydrogonate is not reactive. However, it is very strong, so it can serve as a filler and provide enough strength for concrete. Actually, Raman concrete can easily achieve strength more than 100 megapascal. And next, I will show how we can monitor the kinetic reaction of alkali activation using Raman spectroscopy. Okay. We can use Raman to do many things. For example, we can determine the phases of alumina, silica, and so on. We can analyze alkali activation at room temperature and also detect impurities such as calcite. But the most interesting thing is we can monitor the chemical reaction. We call that dissolution process using Raman spectroscopy. And here shows a picture of samples for Raman. What is the Raman spectroscopy? Raman is a light scattering techniques that can provide us detailed information such as chemical structures, phases, polymorphism, crystallinity, and also molecular interactions. And here shows some example of Raman of different type of samples, including AES flash, Raman, and so on. We also use MATLAB codes to quickly detect and also quantify the crystal phase and also amorphous bandwidth. And here shows complete phase analysis of commercial flash. Okay, we can see different type of phases using Raman. Right. So the most interesting function of Raman is its ability to monitor dissolution process of different phases from the very beginning. So for example, here shows different phases. For example, region 1 here is glassy aluminum silicate, which is, we want to study this phase closely. Also, phase 10, which is here, shows glassy silicate. Okay. This video shows dissolution of flash in sodium hydroxide solution for the first 24 hours. Okay. The dissolution speed changes over time actually, and sometimes even reverse its direction in certain phase. Okay. So you can see going down, sometimes even going up. And here shows the dissolution percentage in the y-axis versus dissolution time. Okay. So this curve kind of reminded me of the classic hydration process of C3S. Okay. Here we can see a competing effect of dissolution and gelation, which is the formation of geopolymer. Okay. So in the first phase, A to B, we see dissolution process increase, which means the concentration of ions increase over time. So precursor dissolved by sodium hydroxide. Okay. Then it achieves its saturation point, and then dissolution process, all the concentration goes down. That means we have hydration product. We have geopolymer form. However, in this case, we have some actual sodium hydroxide which further dissolve the geopolymer. So the concentration of ions actually increase again. Okay. So by doing this, we can get information such as suitability of precursors. It can also help us optimize the concentration and amount of activators. Can also help us optimize the mixing time and mixing procedure so we can reduce the cost and optimize the performance. We can also use Raman to detect the final hydration product of AM. In this case, we have NASH, cash, and also aluminum silicate bonds. Next, I will quickly go over the performance evaluation in the lab before we talk about field applications. And you will see the lab results pretty much in line, consistent with other researches. Okay. So we did fresh concrete tests, including setting time, workability, slump loss, hardened concrete tests, including strength, and some other durability performance. Okay. This is the test for slump. Compressive strength. AEC is very easy to achieve high strength. So the hard part is how we can satisfy all the fresh and also hardened properties, as well as durability, safety, and cost. And here shows the dry shrinkage. Dry shrinkage of AEC is similar to OPC in our study. And here shows result of sulfide attack. Sulfide attack is one of the potential chemical attacks for concrete. And we can see here, AEC is pretty much immune, very high performance to resist sodium sulfate. For magnesium sulfate, the performance is similar to OPC, okay? Because we know for magnesium sulfate, it can attack CSH. And we could have CSH in both OPC and AEC. Okay. And here shows the result for ASR. That's for alkali-silicate reaction, another potential chemical attack for concrete. we can see ASR potential is greatly reduced for AAC, which is, again, pretty consistent with other findings. Here shows the creep result. Creep is similar to normal concrete. This is a setup of a creep test. And lastly, let us focus on field applications in both Hawaii and China. This table shows a case study of flash-based AAC. Okay. It shows us a carbon footprint of alkali-activated concrete. Here, the second column shows ordinary Portland cement concrete. We can see more than 85% reduction in carbon footprint. Cost-wise, in this case, we have 25% cost reduction. In some cases, it may go up to more than 50% reduction in cost. It does not use any cement, so 100% cement reduction. Strength-wise, very good, about 30% strength increase. Fresh property, such as slump and the setting time, pretty much comparable to normal concrete. Shrinkage and creep, similar. Durability tests are all pretty similar, sometimes even better than normal concrete. And here shows the video of pouring the AC. This is in one of the province in China. Here's another video. And early next year, two types of AAC will be poured for Farrington Highway widening project. So this is one of the project from Hawaii Department of Transportation. Okay, so in the first part of 2023. And this is another case study of red mark concrete. This is also in China, around 2 years ago. Another picture of red mark concrete pavement. So here is a short video of pouring the red mark concrete pavement.
1号审销时候，我是用了15%的那个16的水的那一个，效果还是可以。这边看。
Right, so this picture shows the hardened Raman concrete, and we can see we have grass grew by it. So Raman is a high.
有草嘛，
对呀，
是不是？对，不然的话，盐碱地什么都不长。
对呀。
So Raman is a high alkali and toxic materials, which could cause very serious groundwater and soil contaminations. In the city I visit in Shandong province in China, Raman generate saline alkali soil, and basically no plant can grow around there. Rumors said even the local infertility rate was higher because of this polluted groundwater and soil from Raman. Okay. And we can see a lot of grass grew by the Raman concrete. Okay. And here shows preliminary leaching test to confirm the safety of different type of AAC. Okay. It shows concrete made by H-power ash, which is a low quality ash from Hawaii, Raman from China, and also AES flash also from Hawaii. So these two types of low quality ash. So the first column shows the powder. Okay, so how much toxic materials or heavy metals can be leached out from a powder. And the column in the next shows how much materials can be leached out for AEC. Okay, and we can see great reduction, almost go back to zero when we using H power ash versus AEC from H power ash. And also for red mark concrete, okay, as we can see for red mark, it leaves 266 arsenic ppm. And for AEC using red mark, it go down to zero. Okay. Actually, the leaching test result confirm the concrete satisfy the national primary drinking water regulation requirement. So in conclusion, we have some innovative approaches to analyze precursors for AEC. We also monitor the dissolution process using Raman spectroscopy that could greatly help us optimize the concrete mix proportions and also the mixing procedure for AEC. And the field application of optimized AEC could achieve cement-free with more than 80% reduction in carbon footprint, around 25 to 50% reduction in cost. The concrete can be cured at room temperature with very well controlled setting time, flowability, and other fresh properties. It has similar or even better hardened properties, durability, and safety. And we think in many cases, it is mass production ready. And lastly, here shows some of the picture while I visit the site in Hawaii and also in China, okay, some of them during pandemic. And if you have any questions, you can reach me by email, phone number, or my LinkedIn link. Thank you so much.